Section 2.2, graphs of equations. We're going to sketch a graph by plotting points. We're going to find intercepts of points. We're going to find symmetries to help us graph, and we're going to work with equations of a circle. A solution is an ordered pair that makes an equation true. Graph of the equation is a set of all points in the plane corresponding to the solutions of an equation. The y-intercept is where the solution intersects the y-axis. So that means everything along the y-axis, x is equal to 0. So at some point 0y. But usually when they give y-intercept, they'll just give you a number. So that's what y is equal to. X-intercept is where the solution intersects the x-axis. And that's where all the y's are equal to 0. Example, is 1, 1 on the graph of y is equal to x plus 1? Well, remember, this is my x, this is my y. So y, is that equal to 1 plus 2? No. So it's not on the graph, or it's not a solution. I want to sketch a graph of y is equal to negative x squared plus 1. And I want to sketch this by picking points. Later on we will graph parabolas different ways, but I'm going to just pick points. So I am picking an x between negative 3 and positive 3. So my equation then will be y is equal to, negative, my x is only squared, so it's negative 3 quantity squared plus 1. Okay? It doesn't mean negative 3. You're not squaring that negative with that x that you're squaring. It's a negative x squared. This is negative 9 plus 1, which is negative 8. So that's a point, negative 3, negative 8. So do that for all the points. And if you need to pause the video, pause the video. So we're plugging them all in, and we're calculating the points. Once we have our points, I'm going to graph them. So I have negative 3, negative 8. So I have that point. Negative 2, negative 3. I have that point. Negative 1, 0. That's that point. I have 0, 1, which is this point here. I have 1, 0. And now looking at that, I bet there's a point right here. And I bet there's a point right here. But let's see. Is that what I have? 2, negative 3. 3, negative 8. Okay? So the graph looks something like this. It's a parabola that opens down, and you better know it opens down because of that negative, with an x-intercept of 1, 0 and negative 1, 0, so there's two x-intercepts, a y-intercept of 0, 1. And there's the graph. And the right way to do it are arrows because it goes down forever. Another example, find the x and y intercepts of a graph of x is equal to y squared minus 5y plus 6. Y-intercept is where it crosses the y-axis. So remember what I told you? Everything crosses the y-axis, we know something about x. And we know, put it right over here, yeah, x is equal to 0. So if you plug in x is equal to 0, you'll have 0 is equal to y squared minus 5y plus 6. You can factor that. So you do two sets of parentheses with y being your first coordinates. Since this is a positive and this is a negative, the only way to get a positive here would be a plus and a plus or a minus and a minus. But because that's minus, it has to be a minus and a minus. And so now you have to say to yourself, okay, is it 1 and 6 or is it 2 and 3? Because 1 times 6 and 2 times 3 are both 6. But what adds up to negative 5? And I hope you realize that it's the negative 2, negative 3. And now let's solve that. That is equal to 0. So y then is equal to 3, y is equal to 2. So the y-intercepts are 2 and 3. So what you're doing is you're setting that equal to 0 and solving, that equal to 0 and solving. So those are your y-intercepts. Your x-intercepts, where it crosses the x-axis. You know every point on the x-axis, y is equal to 0. So plug in y equals 0. And that's an easy one. And I don't know why I wrote 6. There was a typo here. X-intercept is 6. Y-intercepts are 2 and 3. Reflections, symmetry. A reflection is a mirrored image. The line of reflection acts as a mirror. So here, my x-axis is my mirror. That and that, they mirror each other. So if I had only one drawn, either the top or bottom drawn, and I folded along the x-axis, and it was wet paint, it would mirror to the other one. So if this were wet paint, and I folded it here, the wet paint would go there. Okay? So that's a reflection around the x-axis. And another way, they write it as y is equal to negative f of x. Because y is positive here, y is negative down there. So your y, which is f of x, changes from positive to a negative. So for every point x, y, there is a point down here, which is x negative y. Okay? This graph right here is the graph of x is equal to y squared plus 1. I said notice that it's a mirrored image. If you can't graph it, there's another way to see if it has symmetry around this x-axis. What you can do is where there's x, it stays x, but where there's y, you plug in a negative y. So let's do that. X stays as x, but y, you plug in a negative y. And now let's simplify that. Negative y quantity squared is just y squared. It becomes a positive. So when you do that, when you plug this in, if you get back to where you started from, your original equation, it has symmetry with what you're testing. And here I'm testing symmetry with respect to the x-axis. Okay, so if you get the same equation you started with, it has symmetry. If you get a different equation, it does not have symmetry. A reflection about the y-axis. So for every point here, x, y, here let me draw a point over in the first quadrant, you might see it a little easier. So for every point here, this is an x, y, there is a point negative x, y. Okay, so for every x, y, there's a point here, negative x, y. And here you can see, by looking at it, it has symmetry with respect to the y-axis. But if you didn't know that, then let's take the equation. Wherever there's an x, plug in negative x. Y stays the same. So I have y is equal to negative 3. I plug in negative x. Oops, sorry, to the 6. Plus 2. And I plug in a negative x instead of x. Plus, instead of x, I plug in a negative x. So I have negative 3 times negative x to the 6th power, plus 2 times negative x to the 4th power, plus negative x to the 2nd power. So let's simplify it. So negative 3, a negative to an even power will end up to be positive. Negative to even power ends up to be positive. Negative to an even power ends up to be positive. Now notice, I'm back to where I started from. This equation is where I started from. So that has symmetry with respect to the y-axis. If it has symmetry with respect to the origin, for every point xy, there is a point negative x, negative y. You can graph it. I hope you can see that it's symmetric with the origin, but if you can't tell that, and what it means by origin is everything here maps to here, everything here maps to here. So everything in the first quadrant maps to the third quadrant, everything in the second and the fourth quadrant will map to each other. Okay? So if you can't see it by the picture, let's plug in. Wherever you have an x, plug in negative x. Wherever you have y, plug in negative y. If you get back to where you started from, it has symmetry with respect to what you're testing. So instead of y, I'm going to put in negative y is equal to 2. I have 2x cubed minus x. So instead of x, I'm putting in a negative. Okay, so when I do that, I have negative y is equal to negative 2x cubed plus x. A negative cubed is still a negative. So I'm bringing that negative there. Minus a negative becomes plus. And now, if I either multiply or divide each side by negative 1, I will get y is equal to 2x cubed minus x. Original equation, it has symmetry with respect to the origin. So for every x, y, if it has symmetry with respect to the x-axis, there is an x negative y. So for every xy, it has symmetry with respect to this x-axis, meaning top will reflect to the bottom, bottom will reflect to the top. So for every xy, there's an x negative y. It has symmetry with respect to the y-axis. That means right and left sides will mirror each other. So for every xy, there's a negative xy. And if it's to the origin, whatever's in the first quadrant will map to the third quadrant. Whatever's in the second will map to the fourth. So for every xy, there's a negative xy. So I'm going to use symmetry to graph the absolute value of x plus the absolute value of y is equal to 1. And if you use symmetry to graph it, you can just graph it in one quadrant, check symmetry, and then reflect it. So I'm just going to do a t-table first. Okay? So when x is 0, plug in there, and I have y as 1. When I have x is a half, y is a half. When I have x is 0, y is 1. Okay? So there's my graph just in my first quadrant. Now let's check symmetry. See if it is symmetrical with respect to the x-axis, meaning what's on the top will reflect to the bottom. So to check that, remember, for every xy, every top xy, it's going to reflect to x negative y. Okay? So for x, I'm going to plug in x. For y, I'm going to plug in negative y. Simplify it. The absolute value of negative y is still the absolute value of y. It's the same thing. So yes, it has symmetry. So now I know that what's up here will map down there because of that. Now let me check symmetry with respect to the origin. With the origin, for every xy, there's a negative xy. So plug in negative x for x, y for y. See if you get back to the same equation you do. So that means for xy, I said that there's a negative xy. So this maps to over here. So this maps to here. The red maps down there. And now I really have my whole graph. But you check the origin. Plug in a negative x, negative y for xy. And yes, so this maps to here. And these two map together. Okay, so that's where they reflect. So that's drawing it using symmetry. You don't have to draw it in all the quadrants at the beginning. Draw it in one, and then check for symmetry, and then reflect it. And that's what it looks like. Tomorrow, the next homework assignment will be section 2.2, number 1 through 6, 8 through 56, every other even, and 58 through 66, all the evens.